Very well, we are on streaming now, and I copy the link of the connection of this session on the chat for everyone. And I asked to Francesco to put it on the website and on our channels. Good afternoon to everybody. As you know, I think I am Amedeo Manuello. I'm the chairman of this last session, an atypical session because we don't start with the keynote presentation in this case, because the important keynote of Professor Carpentieri is at the last is the last contribution of the session, because it's a closing lecture. So we can start with the presentation. Stay with us at the end, also after the closing lecture, because we will have the toast of our workshop, of course, and before the toast there is a closing to give some information about the workshop itself. So we can start now with the first contribution by Liguori, Madeo, Leonetti, Magisano, and Garcia, an isogeometric solid shell model for post-buckling optimization strategies. Please, Liguori.
Okay. Hello, everyone. Okay. The aim of the work is to present a numerical model to be used within post-buckling optimization strategies. The main features of this model is that it is able to capture the fully nonlinear post-buckling behavior structure. It allows us to account for the worst case imperfection, and the strategy is applicable to general shape structures. Usually when designing a shell structure, the lowest buckling load is the reference load. However, there are cases in which this load is not a proper safe indicator, as the one reported here in the figure. Actually, also in the case of well-behaved structure, we can have that by taking advantage from stable bifurcated branches, we can exploit extra loading-bearing capability. When making a post-buckling optimization, we have two main issues. The first one regards the discretization techniques, because when designing full-scale structure, we can end up with many degrees of freedom of the numerical problem. From the other side, we have a problem because the evaluation of the equilibrium path can be computationally expensive, especially when the effect of many imperfections need to be accounted for during the optimization. With this work, we propose a strategy that makes use of isogeometric analysis to reduce the number of degrees of freedom of the numerical problem. On the other side, we make use of a specialized version of Coitus method to predict the initial post-buckling behavior. Here there are some details about the solid shell isogeometric model. Everything is pretty standard, exception made for the MIP formulation, that is a strategy that allows us to preserve all the advantages of the use of a mixed format in geometrically nonlinear analysis in a displacement-based model. To perform numerical integration, we make use of patchwise integration scheme. In doing so, we have two main advantages. The first one is that we can reduce the computational cost of the overall formulation, and then by using reduced integration scheme, we can eliminate interpolation locking. Coitus method is commonly used in optimization of shell structures. However, many of the implementations regard simple geometries and simple post-buckling behavior. With the version we used here, we can account for complex shaped structures based on the solid shell description and by the isogeometric model, and capture nonlinear interaction between buckling modes. At the end of the day, Coitus method gives us a reduced system of equilibrium equations that can be easily solved. In this way, the solution of the geometrically nonlinear analysis is made efficient. Another advantage is that by using this method, we can take into account the imperfection sensitivity of a structure on a single run. This is done by searching for the worst case imperfection. This is obtained by a statistical procedure that is based on Monte Carlo simulation. I'm about to conclude with some numerical results. They are about the optimization of a composite wing box made of composite material, of new generation composite material. This is the optimization problem. We want to minimize the out-of-plane displacement of the skin bay under some geometrical, technological, and mechanical constraints. In this picture, I show you some baseline equilibrium path, some reference configuration, and the results about 3 optimization scenarios. Essentially, we played with mechanical properties of the material and by the constraints to obtain different solutions. But in all cases, we can see how we get good improvements with respect to the baseline solution. So we, in a certain sense, we demonstrate that with this solid shell model based on isogeometric analysis and Coitus method, we can optimize a full-scale structure in a reasonably computational time. So thank you very much.
Well, thank you so much, Francesco, also for respecting the timing, of course. Are there any questions for Francesco? No question? So I want to ask, did you try to make a certain concentration of population of defects on your model? And if yes, which kind of effect you have in the post-buckling phase?
Sorry, I didn't understand which effect.
You speak about an homogeneous population of defects.
Yes.
Try to put a concentration of this population, or you are planning to do it?
Well, we used as defect a combination of buckling modes. So it's not uniform because we start with a uniformly distributed population. Then, based on the results of the objective function, we try to focus on the areas of the domain in which we have described the imperfections to find the worst case imperfection. So we start with a uniformly random generated population, but then we evolve towards the worst case.
Okay, thank you so much.
You're welcome.
Question for Francesco.
How do you select the number of modes that you put as a geometrical imperfection?
Well, essentially we try to set up all the analysis by checking that for a certain number of predefined configuration, the number of buckling modes gives the exact post-buckling result, initial post-buckling result. Then we try to use that number of buckling modes to make the analysis at the meantime to build the imperfection population. So it's the number of, essentially, it's the number of buckling modes that we need for the analysis. Of course, we can use more buckling modes, but probably this is not convenient, even if we can increase the population, of course.
Well, thank you so much again, Francesco. Any other question? I think no. So thank you again. Thank you for your contribution. We can move on to the next one by Dimitri and Tornabene.
Yes, I'm here.
Okay. A GDQ-based study of the mixed mode interfacial response of composite specimens with a curved geometry.
Okay.
Nice to see you, please.
Yeah, thank you. Ladies and gentlemen, good afternoon. The main topic of the talk is about a numerical study for the mixed mode.
There is a noise. I don't know why.
Maybe you are in the same room with Francesco, so one of the two has to stop or to lower the volume of the.
Okay. Let's try again.
Better to switch off the volume of one of the two devices.
Yeah. Ladies and gentlemen, good afternoon. The main topic of this talk is about a numerical study for the mixed mode interfacial response of composite specimens with a generally curved geometry, and this work has been performed at the University of Salento in collaboration with Professor Francesco Tornabene. And as you know, the mixed mode fracture mechanics problems and the closed form solutions for non-flat interfaces and adherence with complex materials and geometries are very cumbersome to be approached, despite their great importance for many practical engineering applications, as you can see here. And in this concern, we aim at studying generally shaped composite specimens subjected to an action, transverse and bending loading conditions at one side and clamped to the other one. And please note that the proposed numerical approach, the GDQ approach, generalized differential quadrature approach, enables any kind of boundary condition or loading condition applied on the specimen with a certain flexibility, let me say, avoiding any theoretical closed form computation, both in terms of stress of energy parameters. As you can see here, for example, the same numerical approach could be used also to model simply supported curved beams with a vertical loaded distribution, no? As you can see here in some practical examples of composite arch bridge systems. And let's reconsider our mechanical model. So our case where we consider a layered curved specimen made by two orthotropic sublaminates of general shape, modeled as Timoshenko beams, partly cracked and partly connected by an elastic brittle interface with the elastic constants, both in mode 1 and mode 2, I mean in the longitudinal and in the orthogonal direction. And according to a classical lamination approach, the sublaminates can be modeled as homogeneous equivalent beams, where we have to introduce the following equivalent stiffness you can see here. And we have to define the equilibrium equations for each sublaminate, at least in the adhesive portion. We have then to introduce the constitutive laws for each arm, where together with the boundary conditions, and by combination of all these relations, we get to the following set of differential equations, which are written in a coupled sense. I mean, this set of equations are all expressed by means of the kinematic quantities, both in mode 1 and mode 2, in the longitudinal and orthogonal direction, in a coupled sense. So this set of equations is very difficult to be solved in a closed form solution, in a closed form. And here we provide just a closed form solutions for a simple case. I mean, a straight orthotropic double cantilever beam when the radius of curvature tends to infinite. In this case, we have to apply a suitable change of variables where the interfacial stresses are selected as a primary unknowns. And after a long mathematical manipulation, I don't have the time to discuss about, at the end we have the following set of relations which are uncoupled and easily to be solved. And after integration, we can obtain the closed form solution for the interfacial stresses as well as for the internal forces and the kinematic quantities, as you can see here. Or in the same manner, we can find the closed form solutions or also for all the other quantities in a static and energy sense, which are required to define appropriately the failure criterion to follow the delamination process. And as far as the numerical solution is concerned, the fundamental system of equations together with the boundary conditions can be easily solved in a discrete form by applying the GDQ technique, which discretizes the nth order of derivative of a function as a weighting linear sum of the functional values at some fixed collocation points by means of the weighting coefficients as determined through the recursive formula from the literature. And here are the discretized governing equations of the problem, together with the discretized form for the boundary condition and the constitutive laws. And in a context where the placement of grid points within the domain can affect significantly the accuracy of results, we start the numerical study with a convergence analysis by considering the traction vector along the adhesive interface defined by means of its normal and tangential components, and compute the L2 norm of the error, as you can see here, for different discretizations. Here are the plots in a bilogarithmic way, where you can see the very fast rate of convergence of the numerical solutions for the different discretizations, where it is required a very limited number of collocation points ranging from 65 to 81 in our case to obtain a very accurate results. So in the following, we continue to consider this optimum number of collocation points equal to 65 for our analysis. So now we extend the numerical analysis of the adhesive interface response to curved members with a constant and varying radius of curvature, where you can see here the list of 5 different geometries here analyzed, including the circular, parabolic, elliptical, catenary, and so on, just some examples among some most common geometrical shapes for structural application, where the circular shape is considered as the reference one. And for an orthotropic curved specimen in mixed mode loading condition, we plot the interfacial stresses first against the dimensionless bonding length for this unprecracked specimen and for different curved geometries. And you can notice the coexistence of a non-null value for both sigma and tau for all the geometries, which confirms the mixed mode interfacial behavior due to the mixed mode loading condition, but not only, due to the geometrical curvature. And you can see also the response, the mechanical response in a kinematic sense, where there are all the kinematic quantities are plotted here for different geometries, and where all the curves reflect the great sensitivity of the mixed mode behavior to its geometrical shape, where you can see here has the highest stiffness seems to be reached for an elliptic shape, while the lowest stiffness seems to be reached by a parabolic shape. So, I mean, all the other geometries enable intermediate stiffness values, as you can see here in the kinematic response. So for this limit case, I mean, among a large parametric investigations, here I also show you some results obtained by comparing the elliptical shape against the circular one, so the reference one, for different radius of curvature. And so while maintaining fixed the length span and varying the values of the rise, where the last value of the rise here considered corresponds to the length midspan of the curved specimen. So as you can see here, for an increased value of the rise, both stress components maintain almost the same peak value at the crack tip and decay to zero with an oscillating behavior within a shorter distance from it in a more localized zone. And the effect of the radius of curvature can be seen also here in a static sense and a kinematic sense, where you can see has an increased rise, makes the oscillating behavior of the internal action even more localized. The heft of the crack tip, where an increased value always of the rise increases the overall deformability of the specimens. Look at here, where in particular you can see also has the bolding lines between both for the elliptic and the circular shape are exactly the same, because at least for the last value of the rise, because in this case the elliptic shape tends to the reverse, to the circular one. So we have proved the sensitivity of the response of the delamination response for different curvature and shapes for the curved specimen, which could be, let me say, of great interest for design applications of adhesive joints and curved members. And we have also proved the efficiency of the generalized differential quadrature approach to treat this kind of problems. A possible further extension of the work could include the nonlinear softening branch as typical of a cohesive zone modeling for fracture mechanics problems, and possibly to extend to shell structures, this kind of numerical method. Thank you very much for your attention.
Thank you so much, Rossana. Very, very impressive results. Are there any questions for this paper? No? I have a very quick question. Can the GDQ method have any problem with certain kind of curvature, for example, very high curvature in your opinion, or you can use
No, we can use the method is efficient also for high curvatures, because I didn't show the wider parametric investigations, but we have also further results about this. With any kind of shape, any kind of curvature, so also high curvatures. Yes.
Okay, and very fast, are you planning to make some experimental test to compare your results to experimental observations?
Yes, why not? Because especially because in our university there is an important laboratory where another group really makes this kind of experiments on delamination. Investigations in an experimental way, so we could check our results also with the experimental results.
Well, thank you so much, really. Okay, we move on very fast to the next by Argento, Gabriele, Teresi, and Varano. Shaping by metric assignments. Please, I think Teresi.
Yes, I'm here, but now I can share the screen.
Okay, perfect. Thank you so much.
Okay, good morning. Well, good afternoon, everybody. I start with this slide. It's a comparison between living matter and dead matter. So we are very used to think about loads as a way to change the shape of a solid. An engineer thinks about loading. In the contrary, for living matter, most of the change of shape are due to growth, and growth is very important. And so we want to push forward this idea to change the shape of a solid, thinking about the growth. And growth is a very general word, and different contexts use different words. for an engineer, growth is simply a pre-strain. And the pre-strain can be very large. And here is an example of using pre-strains or also distortion to change the shape of a solid. On the left, you see the huge displacement of a solid, and the right, you see the cause of this huge displacement is a growth, a distortion, which is different along the thickness. So at the bottom, volume elements become larger, and at the top, they become smaller. And because of that, you can change the shape. And it is quite easy to change the shape of a solid using this technique. So now, what is the mechanical meaning of a distortion? So distortion, growth, pre-strain are different words for the same mechanical notion. And the idea is that to add other degrees of freedom to our solid. So instead of describing only the position of a point, we also describe the shape of a volume element. And we also say that this new shape, the distorted shape of the volume element, is a ground-free, is a stress-free shape. So it's the natural shape or the ground shape of the volume elements. So we are thinking only about volume elements. So the problem now is to put together all these distorted volume elements. What is the mathematical representation of a distortion? You can represent a distortion with a tensor field, and for a 3D solid you can represent the tensor field with a 3x3 matrix. So, and here you have the 9 more degrees of freedom, the 9 entries of this matrix, and it's quite easy. Now, in this example, you see on the left you see the matrix. And on the right, you see the deformation that you can achieve with this distortion. This deformation is very large, and it would be very, very difficult to get the same deformation applying loads, because you have to use live loads, and the loads must change during the deformation. So it's very difficult. Using this approach, it is very easy. It is also easy from the computational point of view. And you can get many different shaping. Here you see another very interesting shaping. What you see is a sequence of configuration. Each configuration is corresponding to a given distortion. And what is more important is that this distortion is compatible. It means that all these shapes are stress-free. So there is no stress in this solid. And this is the goal of the growth of a living tissue. Growth must not induce stress in the tissue. You want only to change the shape, but not to change the elastic energy. You don't want to stress the solid. Here is another example. You can design a morphing with distortion. So here is we design the formation of a tube, and you will see how this flat bar will round up on a cylinder, and eventually you get something that very similar to a tube. Again, it's very easy to get this change of shape. Now you can use this technique also for shells, and here is our contribution. And a shell is a very special 3-dimensional solid. So a shell essentially is a surface with an extrusion along the normal, and so you can use this notion of distortion, 3-dimensional distortion, also for a shell-like body. And here you see how you can decompose the distortion field. And behind this decomposition, you can recognize the fundamental forms of a surface. So the idea is that to morph a solid, you need to assign a distortion, which is equivalent to a target metric. Instead, if you want to morph a shell, you have to assign the fundamental forms of a surface. And these two fundamental forms, the first one is related to the membranal strain. The second one is related to the bending, the curvature of the middle surface. You can play with these new degrees of freedom, and for you, these fundamental forms are targets. So what you want to do is to morph a shell such that the fundamental forms of the shell are as close as possible to these two targets, the first and the second fundamental forms. And here is an example, very similar to the previous one. Now I am morphing a shell. So this is a shell. The same kind of morphing that you have seen for a 3D solids. Now you will see it for a shell. And again, the kind of deformation is very large, it's huge, and it's very easy to solve this problem. This is a fully non-linear elastic problem. So it would be very difficult to solve this problem with loadings instead of using distortion or target metrics. And for example, we can curl a shell like this. And again, there is a reference shape and you want a target shape. So you solve a sequence of elastic problem. And each shape that you see is the solution of an elastic problem with a given target fundamental forms. And we can use this technique also, it's my last example, to probe the change of shape from a shell and to use this measurement to deform another shell. So here you see two different shells. One is flat, the other one is curved, and those two are reference shape. And now the black one, I will grow some bubble, and then I want to replicate that bubble on the other shell. And so we can measure the change of curvature on the black shell and use this information as a target metric for the purple shell. And you will see this bubble growing on the shell. And what is interesting is that on the black, on the source shape, this deformation is given and is compatible. So there's you simply have a bubble on a flat surface. Instead, on the other shell is not compatible, and you will see here a buckling around the bubble. And this is my last slide. The final slide is just references, and I thank you for the attention.
Well, thank you so much, Luciano. Very interesting approach. Very interesting method. We have a question from Professor Luciano Rosati. Please, Professor.
Il microfono, professore.
Hi, Luciano.
Hi.
Congratulations for your very interesting presentation.
Thank you very much.
And just a question, were you motivated by an intellectual curiosity, or are you thinking about some specific applications? For instance, how do you apply that kind of distortions, very nice and very interesting distortion, by actuating the structure in some way, or what else?
Okay. First of all, this work has been done with other people, and I want to thank Stefano, is one among the authors, also Valerio Varano and Gloria Rito Argento. So it's a group of people, because it's not so easy to solve this problem. And it's not me, but we are a group. And the motivation, initially the motivation was to transport the metrics. So we started from the last slide. And the idea was to reproduce shape changes on different surfaces. So I probe, for example, with the camera, I take the evolution, with a movie, deformation from a source. Then I want to apply that kind of deformation to another different surfaces. So this was our original idea. And then we discovered that with this tool, we can morph very easily a lot of shells, but also solids. So now we are thinking about using this technique also for form finding.
And could you be so kind to send me the list of references you showed in your last slide?
Oh, yes, sure.
I'll send my email on the private.
Okay, yes.
Privately.
Thank you for your interest.
Can I add a comment?
Yes, of course, Stefano.
Thank you. Because if you go, Luciano, to the slide in which we have the expression of the fundamental forms of the metric.
Mm-hmm.
Because in this way we found a way of we are able to calculate the target metric. The idea for finding, for instance, is to try to see when some terms here disappear, and so which kind of also mechanical property could have the obtained surface, and if it is possible to also to obtain according to boundary conditions also that could be taken into account, of course. So of course this is a work in progress.
Okay, thank you.
Well, thank you so much again, Luciano. And we move on to floating bending tensile integrity structures by Giannetti and Micheletti.
Yes.
Please, Andrea.
Yes, I need to move this. Can you see my screen?
Yes, very well.
Can you hear me clearly? Okay. So I'm presenting a joint work with Ilaria Giannetti, and we are both from the Department of Civil and Computer Science Engineering of University of Rome Tor Vergata. It's a conceptual work about floating bending tensile integrity structures. And so it comes from the observation that if you have a diamond type tensegrity structure, we can see this diamond shape formed by this four cable connected to one of the bars. And then you can see some similarities with arch-supported membranes, like this one I sketched here. So the idea is to modify the tensegrity modules with this by curving the struts and adding the membranes. So we patch each diamond of the module with arch-supported membrane, and by doing so we can transform for example, the classical T3 module, which is a well-known tensegrity modules, into this structure. And then here I put again the classical T3 module to compare the figure to see that the internal volume is much larger. So one of the features of this tensegrity module is that the bars are always inside the structure and cables outside, and then it's difficult to exploit them. And so to exploit the internal space. So they are very good for deployable system, for shape-changing system, but the internal volume is, let's say, they have these elements inside. So in this way, you have a usable volume inside. So this is the main advantage. And it's a freestanding structure. So the other feature is that there is no contact between the stiff, the rigid element or stiff elements in bending. And the difference is that these members are subjected to bending and of course also to shear and torsion. And then so the name, we preserve the tensile integrity of cables and membrane, and we suspend the arches. So first thing we did is to try to do the form finding in the simplest possible way. We use a MATLAB, and then we use the membrane elements and cable elements as simple constant stress elements, and we added the stick and spring element, which for the arch. Basically, it's a normal linear element, but we attach to it two springs. One which, let's say, we have a spring between one element and the next one, which takes into account the bending with this rotational spring. And also, if you have three consecutive elements, we consider the dihedral angle, which we can define with three elements. And so there is another spring. And in this way, we have a simple model. We can minimize the elastic, it's a linearly elastic model considering in a large displacement regime. And so we minimize the energy and we find the equilibrium shape. And so this is the result for the example I showed before, and then yes, you see this is the equilibrium geometry we obtained, and then we did the same with another module, which is a T4. It's called T4 module, and then. This is one first approach. Then after this, we saw that there is an equilibrium shape. We use a better, let's say, a little bit more easy to use model, which is this one with the commercial software WinTest, and we used it in combination with the Rhino and the Grasshopper. And so with this software, you can import a mesh which we generated with the other two softwares. And I would like to thank Professor Ramon Sastre from UPC in Barcelona, because he kindly provide us an academic license to use this. And then we try to see some simple applications to use these shapes for some architectural application. This is for a pavilion, and this one can be, for example, for social distancing. And then let me go quickly. Here we put a series of classical modules. They all belong to the diamond class type. So we can modify them in this way. For example, this one, we can transform it in a floating bending tensile integrity structure. And then tensile system are sometimes have been regarded as balloons by Buckminster Fuller, because you always have tension outside and compression inside, like in a balloon under with some compressed air inside. And this structure you see here, it looks very complicated, but it can be generated by this simple seed structure. So this is a perspective view. This is the top view, and then you can see this arrangement of parts. You can see a square, so you can imagine any polygon here, or polygonal, pseudo-polygonal shape there. And then you can have several layers, so you get this kind of shape. Then maybe you can, this is a freestanding structure, maybe you want to use this as a covering. So something you can do is to section a portion of this structure and then constrain the section at the points to the ground. And this is one of a nice model which was built by Davide Cadoni several years ago. And then, so you can see here, you can also imagine that you can transform this into a floating bending tensegrity structure. And also in the same period, there is this very nice installation by Kazuhiro Kojima from C+A in Japan. I think it's also in the students from the School of Architecture in Tokyo, they participated to this project. It's very nice. And so in here, the rigid elements are inserted into some pockets into the membrane. So this, and of course, there is bending in this element. So this can be a floating bending structure with, it can be regarded as a floating bending structure with straight elements. And then that's all. We are trying to study this problem. It's very interesting because let me go back a second to this one. You can see here a continuous surface, pre-stressed surface with singularities. There are two types of singularities, one for the cable, one type for the cables, the other for the arches. So the general question is,
you are over 9 minutes.
Okay.
Don't worry, but only to give a warning.
Yes. Yeah, so the general question is what are the possible surfaces, which processable surfaces of this type? And these are some references where from Takatamis and probably Larsen and also Shigematsu and others with tensegrity membrane structures and fluid elements. And tenserity, which there you also have this structure contains it's an inflated balloon with reinforcement, so there is some similarities. And this is a nice pavilion which was awarded last year at the IWSS in Barcelona, which is not a diamond type, however. So the question is whether you can transform this into a floating bending structure. So the main questions are, can we have funicular arches? Or in any case, we would like to minimize bending and torsion in these elements. And also we need to study buckling and superstability of this. Superstability is something well known in the literature. And also we would like to do a trade-off analysis between structural efficiency and deployability. And so I want to thank again Professor Ramos Sastre and also Diana Peña for how to use the software, and also Professor Fraternali for some useful comments during the preparation of this study, and also the students who work on this subject over the years. Thank you very much.
Thank you so much, Andrea. We have a question from Francesco Marmo. Please, Francesco.
Okay, Andrea, thank you for the beautiful presentation. I like so much your idea of combining bending and tensegrity structures. And my question is about form finding. So usually form finding can be done with a force density method in which you linearize every equation. But what happens if in case you have angles as a parameter, can you linearize equations? And
yes, so you need to redefine a stress, define a generalized stress matrix, which is something I'm trying. I started working on it, so it should be possible. I don't know if you get a linear equation, but it's probably you need to switch between. There are some technique for form finding. The problem here is you have simultaneously tension and compression, so it's a little bit more complicated with respect to tensile structure or masonry structure. And then you need, usually what is done is to switch between equilibrium operator and stress operator, which are defined as, these are known terminology in the literature. And so you need to define a stress operator. Equilibrium operator is easy to generalize it in this case, but the stress operator is a little bit harder to generalize for these stick and spring elements. For example, yes, that's quickly a quick answer, let's say.
Thank you very much.
Thank you so much. For timing, I kindly ask you to Rossana Dimitri to post the question to Andrea by chat, please, because we have to move on. Thank you so much, Rossana. Sorry. Okay, we move on for the other presentation. Parametric design of optimal long span hollow section steel beams by Fiore, Tarallo, and Marano.
Okay, good afternoon to everyone. Just one moment.
Yes, you're welcome.
Okay.
For sharing, you have the green button.
Yeah. No. No, just one moment. Okay. Do you see my presentation? Do you see?
Yes.
Okay.
See the PowerPoint.
Perfect. Okay.
Put it in presentation modality, I think.
Yes. Okay.
Well,
this study deals with the weight minimization of planar steel beams. Circular hollow sections are considered. This is due to the excellent mechanical properties of hollow members, in addition to the beauty and lightness of their shape. In fact, the use of hollow trusses increases the resistance to buckling, and it also allows to modify the cellular density without changing the cell size or the truss slenderness. The design optimization refers to size, shape, and topology. The optimal solution is obtained by a differential evolutionary genetic algorithm named Galapagos, where a suitable combination of mutation crossover operators is adopted in order to achieve the best solution. The Galapagos solver is implemented within the Grasshopper working environment, an innovative parametric Rhino design tool. The analysis concerns three different typologies of simple supported steel beams, a truss scheme, an arch with orthogonal ropes, and a network arch. The span length is equal to 20 meters. So starting from the truss scheme, after implementing the geometrical model by the workflow in Grasshopper, and in the same way the constraints and load, that is an initial configuration with the loads, the minimum weight optimum design is pawned as a single objective optimization problem, subject to constraints formulated in accordance with the current Eurocode 3. So we can formulate the optimization problem as find the best vector of input variables to minimize the weight, satisfying the constraints imposed by Eurocode 3. So here you can see the optimization algorithm, and in this case the design input variables are represented by the geometrical dimensions of the cross sections of the different components of the truss, by the outer and internal arrangements of elements. This is the optimal configuration, and these are the circular cross sections, the optimal circular all sections selected by the algorithm, and these are the normal and bending stresses. The same procedure is applied for the arch with the orthogonal ropes. And so after definition of the geometrical model of constraints, loads, and then of an initial configuration, and these are loads, then the optimization procedure is run. And in this case, the design variables are represented by the cross sections of different components, by the arch curvature, and by the internal arrangements of elements. And in this case, this is the optimal configuration, and with the cross-section according to Eurocode 3 prescriptions, and normal stresses and bending stresses. Finally, also the network arch is analyzed in the same way, and again, also in this case, the design variables are represented by the cross sections of different components, by the arch curvature, and by the internal arrangements of elements. This is the optimal configuration with cross sections and normal and bending stresses. By comparing the previous results, some consideration can be drawn up. The network arc, in fact, results to be the best among the best solutions, since it is characterized by the minimum weight and stresses. Moreover, the optimal solution is current with some previous literature studies we have carried out. In fact, the cross-section of the arch results to be bigger than the one of the bottom chord, as well as diagonals are characterized by the smallest values of the cross-section width and thickness, according to the distribution of intensity and stresses. In addition, the optimal configuration confirms that the optimal arches are always rather shallow, in accordance with some analytical evidences we recently achieved. Thank you for your attention.
Thank you so much, Alessandra, also for try to respect time.
Yeah.
Are there any questions, please? Okay, from Giovanni Garcia.
Okay.
Giovanni, you can make the question by yourself.
With respect to the buckling of each member, without considering the possibility to have coincident buckling mode, you can have a structure optimized at all at the end of your process, because you can have coincident and structure sensitivity. Okay, you consider this aspect in your work or not?
Can you repeat the last question? The audio is not perfect.
May I reply directly, Alessandra?
There was some problem with the audio, Giovanni.
Yes.
Can you please repeat?
I can read the question.
I write the question in the chat. I don't know if there is.
Okay.
I read it. If you optimize with respect to the buckling load,
okay,
you can have coincident mode, and the overall structure could not be optimized at all. Consider this problem in your work.
Yes, there is within the verification imposed by Eurocode 3, there is also the buckling verification. So inside the force, because there are technical codes from different countries, the solution is verified according to the technical code prescriptions, and in fact also buckling is considered.
Thank you.
Buckling, tensile verification, also verification of deformation, everything.
Thank you,
Thank
Alessandro.
you.
Okay.
Okay, we can move on. The next paper, please. Analysis of novel adaptable tensegrity towers by Fraddosio, Micheletti, Pavone, and Piccioni.
Okay, good evening.
Good evening. Gaetano, you can share your screen. Thank you so much.
Okay. Okay, can you see my presentation?
Yes, very well.
Okay, thank you. Thank you very much.
Yeah,
Okay, good evening to everybody. I'm Gaetano Pavone, Researcher Department of Civil Engineering and Architecture of Polytechnic University of Bari. In this presentation, we'll talk about analysis of novel adaptable tensegrity towers made in collaboration with Aguinaldo Fraddosio, Andrea Micheletti, and Maria Daniele Piccioni. The present work explores the capability of novel expanded tensegrity towers to be a cable-driven shape-changing structures. To change the shape of the tensegrity structures, active and passive cables are used. Thus, our objective is to investigate the use of tensegrity structures as a foldable deployable system or for smart and adaptive structures whose member can act as sensor and/or actuators. So, at the left, the module of the tower is composed of 8 struts forming 2 sets of 4 equal length compressed elements and connected by a vertical cable, 4 horizontal bottom and 4 horizontal top cables, and 8 diagonal cables. Such elementary tensegrity cell has 1 self-stress states, no null in every element and no mechanisms in a 3-dimensional space. And also it can be noted that the elementary tensegrity cell is a not superstable tensegrity structure. 3 parameters describe the geometry of the cell. In particular, H is the height of the pyramid formed by a set of 4 struts. R is the radius of a circle circumscribing the nodes of the cell in the XY plane. And finally, D is the length of the vertical cable. The modular tower analyzer is composed of 2 modules sharing 4 horizontal cables. And the tower has 4 independent self-stress states and no mechanisms in the 3-dimensional space. The self-stress states are not localized in each module. Indeed, each of them involves different elements on the tensegrity towers. This implies that to change the length of a not shared element, it is necessary to adjust not only the length of the element belonging to the same module. Support conditions of the tower are located at the base node, and the tower is opportunely constrained to remove the secret rigid body motions in the space. Moreover, such tensegrity tower is not super stable tensegrity. And then different novel shape-changing expanded tensegrity towers can be designed by choosing appropriate sets of active and passive cables, respectively, in order to achieve various configurations. And so to this work, we are interested in seeking how it is possible to obtain different shape changing by means of the use of the minimum number of active cables. It is worth to note that to specify that active and ordinary cables have the same material stiffness properties, and in contrast, passive cables are characterized by very small Young modules. Then initial symmetric self-stress stable configuration can be obtained by applying an initial press strain at symmetrically placed passive cables equal to 0.2. Shape change of the towers can be obtained by shortening specified active cables or of a predefined amount equal to 0.4. In this preliminary work, we focus our attention on the following shape changes: stretching, shrinking, flexure, and torsion. Stretchable tensegrity towers are characterized by the fact that all the elements tend to linearly increase their axial forces. In particular, struts, shared horizontal cables, and vertical cables achieve an internal forces higher than the initial stress up to 50%. A slight variation of the tensile internal forces can be observed in the remaining horizontal and diagonal cables. And the total elongation of the structure, equal to about 13%, can be measured for these towers. Shrinkable tensegrity towers show different behavior of the struts. In particular, compressive internal forces in the outer struts are greater in absolute value than those of inner struts. Moreover, inner struts and vertical cables have the same behavior in absolute value. In particular, their internal forces increase until actuation strain is smaller than about 0.2, and then they decrease. Shared horizontal cables increase their tensile internal forces of about 50%, and moreover, the length of the shared horizontal cables increase of about 15%. For flexing tensegrity towers show that axial forces in vertical cables increase, and axial forces in the elements are strictly related to the choice of active and passive cables. In this example, we consider, for example, one of the shared horizontal cable as an active cables. But we can also choose different active cable, different sets of active cable. In particular, in the left, we have two shared horizontal cables are considered as active cables. At the right, we have three shared horizontal cables in order to manage the direction of the bending and of the flexing of tensegrity towers. Finally, twistable tensegrity towers are characterized by a clockwise rotation of about 5 degrees. Bottom struts increase their compressive internal forces in absolute value, while internal forces in the top struts slightly decrease. And it can be observed that cables belonging to the bottom module increase their internal axial forces. This is due to the activation of the bottom active cables. Finally, preliminary analysis of shape change of novel adaptable tensegrity towers have been performed by means of cable actuation. And different kinds of shape change have been considered, like stretching, shrinking, flexure, and torsion. And the choices of the active cables as well as of the passive cables satisfy the following criteria: minimum number of active cables and passive cable placed in symmetrically position. Further analysis will be conducted in order to investigate the influence of the geometrical and material parameters on the shape change capabilities of the tensegrity towers. And moreover, different topologies can be considered for the elementary cell of the tower with the 2, 3, 6 struts joined at the nodes of the vertical cable respectively. For example, in this slide, we can show how the novel expanded tensegrity cells can be assembled for a tower with 2, 3, 4, and 6 modules assembled in a longitudinal way. And for example, a grid with 8x8 modules. And then the determination of the minimum number of active cables allowing for multiple shape changings and the effects of different load conditions will be numerically and experimentally investigated in our laboratory at the Polytechnic University of Bari. Thank you for your attention.
Thank you so much, Gaetano.
Thank you.
Very nice work, very interesting. I have a question from Ramarao Mallela. I read for you.
Yes.
Strong are the tensegrity towers with respect to the torsion. In case this tower can resist torsion, perhaps they can be used to resist torsion due to wind loads subjected to hurricanes, cyclones.
Oh, okay. So this is a preliminary work, and effect of different load condition will be numerically investigated in the future. So if we can consider the condition, the load of due to wind load subjected to hurricanes and cyclones, we have to perform a filter analysis in order to investigate this kind of loads.
Thank you so much.
This is still an exploratory study, so this actually, yeah, we didn't put wind load yet on the towers. But of course, if you make it big enough, the elements, and strong enough, it depends how much big. Maybe if it weighs more than conventional,
yes, of course,
structure, maybe it's not convenient. Let's say these towers are good for soft robots,
yes.
so that maybe for human interaction, they can get stiffer or softer according to various situations. That's the preferred application in the literature.
Yes, of course. Thanks, Andrea.
And Andrea. Okay, we can move on. Very interesting paper entitled Virtual Element Method for Solid and Structural Mechanics by Edoardo Artioli.
Thank you, Mr. Chairman, and good afternoon, everybody. I would like to thank my colleague Andrea Micheletti for the nice invitation, together with the whole organizing committee. I would like also to acknowledge my co-workers that are listed here, and to whom many of the following results and developments my presentation is starts with giving some brief details on the virtual element methods, and to make things simple, I will just stick with equilibrium of 2D continuum bodies, possibly exhibiting nonlinear inelastic material behavior. I will just try to keep the discussion the least possible technical for the presentation not to be too boring to anybody. And subsequently, I will just present some applications that we have been working on in the recent years, trying to show the main features of this relatively new method. And finally, we'll draw some conclusion. So just to give an idea, here are the first papers on the method, the seminal papers by the group of numerical analysis led by Professor Brezzi and Professor Beirao in Pavia. They are basically the inventors of the method, which is, as the name itself reminds, a numerical tool for the numerical approximation of PDEs. So sticking with an equilibrium problem for two-dimensional material bodies, we have a variational formulation for this problem, which is provided by the principle of virtual work. And if we work in a primal setting, we end up with a variational formulation for the displacement. And very much in a similar fashion to standard finite element analysis, we build a discrete form for this statement by constructing discrete approximation spaces for the unknown, for the displacement field, and we restrict the variational formulation to this discrete setting. So when we go to virtual elements, and we do so, we first start from considering a simple polygonal mesh of our reference domain, which is any sort of a subdivision of the body domain into non-overlapping polygons with either straight or curved edges, as we have here in the sketch on the upper right part of the slide, where we have the unit square, which is discretized by a Voronoi castellation. So that's the kind of mesh we're looking into when we deal with virtual elements. And as I said, very much in the classical FE fashion, we build local approximation for our displacement field, starting from the element level, from the polygon level. We call it the virtual admissible displacement field, VH, and this is built up choosing for a positive integer k, representing the order of accuracy of the method. And this is the collection of vector valued functions that have sufficient regularity over the polygon domain and are defined as follows. They have a Laplacian, which is a polynomial of degree up to k-2 and over the element, and are a polynomial of degree k over the element boundary. That is all we know about our virtual element functions. So the idea is that for functions VH, we have that they are totally known explicitly on the element boundary. They're fully implicit, meaning not known inside the element, and they are globally continuous over the element boundary. A picture that I like to show at this point is the following, which basically emphasizes that with this kind of method, we have a relaxed mesh conformity concept, allowing for, as you can see here, hanging nodes, just to mention one key feature of the method, which is rather different from standard finite elements. Again, very much in FEM fashion, we have a FEM-like representation of the unknown field, namely the discrete approximated displacement will be a linear combination of some virtual shape functions through local degrees of freedom, which are defined with respect to the order of the method. So for instance, looking at the pentagon on the right column, if we do linear virtual elements, we have that our degrees of freedom will be the local values at the vertices of the displacement. If we go to quadratic, we have also local values at the edges midpoints plus the average over the element. If we go higher, we have more degrees over the edges of the element and higher moment over the polygons. So everything, if you can see, is pretty much in the fashion of standard finite elements, and the construction of the global space of approximation is done in the classical fashion, namely by gluing with C0 regularity at the inter-element boundaries. We have tested this method in conjunction with material nonlinearity, and we have basically made a numerical campaign over classical benchmarks. Here I'm going to show you just a couple. This is a classical benchmark from plasticity. It's the perforated plastic strain under the plane strain solution assumption. We tested here different meshes, different loading conditions, and we compared with reference solution obtained with mixed enhanced finite elements. Another illustrative example is taken from shape memory alloy materials. It's a simple thermomechanical actuator which exploits both shape memory effect and superelasticity, undergoing a thermomechanical loading cycle. And as we can see here, we have a positive comparison with reference solutions as well. So the main message from this quite large gallery of numerical experiment is that we have somehow assessed the method accuracy, precision, and robustness, its versatility with respect to the chosen constitutive model, and we have basically found that the method shows low to no sensitivity with respect to mesh distortion, and more importantly, anything connected to a standard nonlinear FEM implementation can still be retained. Another interesting application that we have been recently working on with the group by Professor Riggers in Hanover is the development of virtual elements for computational content mechanics problem. Here we see a couple of standard benchmarks, the classical Hertzian content problem and a more sophisticated problem related to an elastical indenter which penetrates a spherical substrate. We have developed curvilinear virtual elements, and we have exploited in this framework some of the key features granted by the method, which are local mesh refinement and the possibility of inserting knots at the curved interface of a contact between the two bodies, which proved quite efficient in regard to available contact algorithms. Moving on, another interesting area that we have been recently working on with Professor Sacco from the University of Naples, Federico II, and Professor Marfia from the University of Roma III is the development of a band-based fracture path tracking algorithm for 2D cohesive fracture. Here again, you can see that we have exploited some of the key features granted by the method, basically the possibility of dealing with evolving interfaces within the domain of interesting, and also the possibility of having refined forward and backward mesh refinement strategies for I would say, efficient fracture path tracking algorithm. Another interesting field that we have been involved recently is related to the computational homogenization of fiber reinforced composite materials, either with a double periodic arrangement or in a random arrangement. Without giving too much details, this problem again leads to solving a standard elliptic problem over a complex 2D domain, which is represented here, which is the unit cell domain for the composite material. And we proved that using virtual elements is quite an efficient strategy to derive the solution to such a problem for many reasons. As you can see here, we have basically a very similar construction of the method with respect to the initial case. In this case, we have the capability of exactly reproducing the curvilinear geometry of the interface between the fibers and the matrix. And pretty much everything is very close, very similar to the initially presented construction. We have tested the method for different types of meshes, for different orders, higher orders, confirming accuracy and convergence. And lately, with Lorenzo Beirao and Marco Verani from the Politecnico in Milano.
You are over 10 minutes.
Okay, just one more slide, and I'm done. Yes. We have extended the analysis to random composite materials and to more involved complex fiber cross sections, getting quite good results as well. The last application, which is related to plate problems, is done in collaboration with Professor Taylor and Lorenzo Beirao, and is basically a technique that we have devised, borrowing the so-called linking approximation from finite element analysis, which in this case proved quite efficient in deriving shear locking free plate virtual elements. Just a very quick conclusion, we have that we think that the VEM is a numerical tool with a potential in solving applied mechanics problem, and that there are many features that make it quite interesting as a potential alternative to standard finite element method, and that there's a lot more to be explored in this field. Thank you for your attention.
Thank you so much, Eduardo. I think you have really an encyclopedic knowledge about virtual element method. Are there any questions about this very interesting paper? No question. So if you have a question, please post on chat and we move on. Sorry, Eduardo, because we are a little bit late.
Sure.
Okay.
Thank you.
Thank you so much. The next paper by Luigi Fenu, Eleonora Congiu, Giuseppe Carlo Marano, and Bruno Brisighella, Carved Shell Supported Footbridges. Okay, Luigi is the presenter. Is it right? Luigi, is possible you have the microphone turned off?
I think now it works.
Okay, very well. Thank you so much.
Thank you. Sorry. Sorry, ladies and gentlemen, good afternoon. This presentation is a summary of our research in shell-supported bridges in the last 15 years, maybe. And we initially followed Musmeci work, and he shaped his shell bridges using many methods, for instance, soap bubbles, differential equations, rubber physical models, and always starting from shaping shells with isotropic curvatures, and then by changing the transverse curvature. And initially we shaped some footbridges following Musmeci's method. And then we also applied topology optimization coupled with the form finding procedure. And then we turned to curved shell-supported footbridges that were mainly shaped using a particle spring system. And sorry, there is a problem with the video. Okay. Oh, okay, because I didn't see the video. Your faces were hiding the video. Oh, and then besides the particle spring system, we also used a non-standard thrust network analysis and compared the results. And finally, now we are studying the seismic form finding of curved shell-supported footbridges, mainly using a particle spring system. And here we see our initial work following Musmeci's work, Musmeci's method of shaping an isotropic surface and then reducing the transverse curvature. And some years later, the year later, we tried to follow his method and to shape a footbridge. And we also studied how to build it by using ferrocement and by using, for instance, initially a tension structure made of steel wires, and then obtaining ferrocement and so on, and then by spraying the concrete to finally obtain the shell. This work is of 2005, and this is the footbridge. And then we applied topology optimization and together the form finding method. And this method was also applied to a real bridge, the Sandona Bridge in close to Venice. And then we studied curved shell supported footbridges. Here we see how to apply the boundary conditions. And here we see we use the particle spring system and using an auxiliary tension structure that you can see here. Here we see a photo montage, a perspective view of the foot of the shell supported footbridge, and also detailing of the deck that is a cantilever deck, and then we needed to apply pre-stressing and to exploit the ring shape of the girder. And we also used the TNA, the thrust network analysis, but we had to use it in a non-standard way, because in the standard block way of performing TNA, we cannot apply to a surface whose projection is superimposed, and while in the horizontal direction the bridge, the shell of the bridge has not superimposition between the different parts of the shell, and so we applied the TNA in the horizontal direction, and then we checked by finite elements with the actual vertical loads, and then again in a loop until we find good results. And here we see what are we doing now. For instance, a shell supported footbridge with curve and the counter curve of the deck in some way following Schleich's work. And here we see the for finding under both vertical and seismic loads. In particular, we are investigating how the seismic loads affect the shape of the shell supporting the deck. Of course, it is necessary to the deck is not imposed as in the previous example, but the shape of the deck is affected by the seismic loads. And so we see how increasing the seismic loads affects the shape of the shell and of the deck. Thank you for your attention.
Thank you very much, Luigi, for your presentation. We have a question from Francesco. Please, Francesco.
Thank you for your presentation, Luigi. So I find beautiful the choice of having a deck that is actually a cantilever, but it is acting in torsion on the membrane. Did you account for that torsion?
Of course, because
the form finding.
Yeah. You know, in the form finding, not because actually the deck was hinged. So the cantilever is hinged to the shell.
And so who cares about the torsion? Which part?
Torsion, we pre-stress the girder. And since we pre-stress a ring girder, then we can counteract the torsion.
Okay.
Exploiting the properties of ring girders.
And another thing, the seismic action, of course, is acting in both directions.
Yeah.
Both positive and negative. Did you account for both, of course?
Oh, of course, yeah.
Okay.
Okay.
Thank you.
Thank you.
Thank you so much, Luigi. Again,
Okay,
are there any questions for Luigi? No question? Okay. Thank you so much again. Very nice presentation.
Thank you.
Well, and now for me, a very expected moment. There is the time of the last keynote lecture, the closing lecture by Professor Carpentieri. Professor Carpentieri, are you there? Can you switch on your microphone and cam, please? Professor Carpentieri, are you there?
Can you hear me now?
Yes, yes, Professor.
Yes, okay.
Very, very well. Okay.
The slides, you can show.
Yes, yes, yes. I want to introduce you before. Of course, is a great pleasure for me to introduce Professor Carpentieri. I have to say at the beginning that he's for me a point person from the academic point of view. He moved to the Politecnico di Torino in 1986 as a full professor and became the chair of solid and structural mechanics, as well as the director of the fracture mechanics laboratory. During this period, he has held different positions of responsibility, among which head of the Department of Structural Engineering and founding director of the Postgraduate School of Structural Engineering from 1990 to 2014. Professor Carpentieri was a visiting scientist at Lake University in USA and was appointed as a fellow of several academies and professional societies, among which the European Academy of Science, the International Academy of Engineering, the Turin Academy of Science, the American Society of Civil Engineers. He is presently the head of the engineering division in the European Academy of Science. Professor Carpentieri was the president of different scientific associations and research institutions, the International Congress on Fracture, the European Structural Integrity Society, the International Association of Fracture Mechanics for Concrete and Concrete Structure, and others. He's member of the editorial board of 15 international journals, and is the author and co-author or editor of about 1,000 publications, of which more than 400 are papers in referred international journals and 54 are books and journal special issues. Professor Carpentieri, finally, received numerous honors and awards, such as the Robert Lermite Medal, the Griffith Medal, the Paul Paris Gold Medal from ICF, the Doctorate Honoris Causa in Engineering from the Russian Academy of Science. Well, and the title of this closing lecture is Funicularity in Elastic Domes, Coupled Effects of Shape and Thickness. Now I share the presentation for Carpentieri. 1 second. Okay. Okay, Professor Carpentieri, I think that you can see in the monitor your presentation.
Yes, I can see.
When you want to move on the slide, you can say me next.
Yes, thank you very much. Thank you very much. Good afternoon to everybody. I have to thank the chairman for the very nice introduction. and also the organizers for inviting me to give this talk. Yes, the title was already read by Professor Manuello. I can add that the main goal of my presentation is to show how much important is the static kinematic duality to put this problem in a rational way. My co-author is Dr. Federico Acornero, who is in the audience. Next, thank you. Next. So this is very general concept. So I start from the most simple example usable for our goal is the rectilinear beam. Is very well known, but we introduced the symbol and the concepts. You see three equations. They are the three equations of indefinite equilibrium. The first is, of course, the equilibrium to transverse translation. The second to axial translation. The third to rotation about yes, the rotation. We are in the plane, of course. So the symbol represents T is the shearing force, N is the axial force, M is the bending moment. You have these operators, they are derivatives of the static characteristics. And in this equation, Q, P, and M are the distributed loadings. The next, thank you. So this is they are the same equations, but reported in a operator matrix form, which is very interesting because we immediately see that they are three equations in three unknowns, T, N, and M. Is in some way we can say is isostatic, or better to say statically determinate problem. So it means that we can solve the problem of the beam only by statics. And you see that it was very interesting that the three operators, the derivatives, are on the diagonal of the matrix, 3 by 3. And only one algebraic term is present in the matrix, exactly -1, which obviously is related to the fact that the shearing force is the derivative of the moment, as everyone knows very well. But it's a quite original way to present the problem. Please, the next. About the kinematic problem, we see that it's very important to define gamma, y, sub y, if you want, but gamma is the shearing strain. Phi, in the second sketch on the right, phi or phi x is the rigid rotation of the beam segment. And through these two quantities, we can define the differential of the transverse displacement. You see dv, which is the summation of the two terms. And finally, we have that the derivative of the transverse displacement with respect to z is equal to gamma minus phi. It's important to observe that gamma is a deformation and phi is a generalized displacement. It's not a marginal thing. Okay, the next, thank you. So they are the kinematic equations. It means the definition of the three deformation is shearing strain, axial dilation, and curvature through the three displacement. No, V is the transverse displacement, W is the axial displacement, phi is the rotation. And in between there is the kinematic matrix, which is in some way we can say the transpose of the previous one, the static matrix. But there is a difference. We have all the same, the three derivatives on the diagonal, but the unity In the first case, it was a -1, so negative. Now it's positive. So the rule is that we have to change. There is a very important reason that I cannot have not the time to explain, but we can say that we have to change the algebraic sign to the algebraic operator. No, you see that of course the derivatives don't change their sign. Okay, so there is a strict relationship which we call it static kinematic duality. So the next, thank you. What happens when we have a curvature? The situation is a little changing, not so much. You know that we have three equations of equilibrium, very analogous to the previous one, so I don't explain in the detail. We can see only the differences between this situation and the previous one. I can say that the axial coordinate z is substituted by s, which is the curvilinear coordinate. R is the radius of curvature that before was infinite, of course, and the theta is the angle around the center. The substantial difference is that we have two terms more. You see, in the first equation we have minus n over r. In the second equation we have plus t over r. No, the other terms are about the same, of course. The next, please. So you see that I put also in this case the equation in the operator matrix form. The significant, the meaning of the symbols is about the same. So I don't need to explain too much. We have the derivatives along the diagonal. We have -1 in the third row, first column, but we have two terms more. Now you see 1 over r in the second row and -1 over r the first row. Now they are due to the curvature, of course. And we see that also the curvilinear beam is isostatic. It means statically determinate, no? Because we have three equations in three unknowns. Okay, the next, thank you. About the kinematic problem, we have to distinguish, of course, they are represented here, two fundamental situations. The first, on the left, represents a uniform displacement, axial displacement, tangential displacement W. And you see that in this way, you have, as a result, a rotation. A rotation is produced by a uniform. It's a uniform, of course, because it's a very short segment, curvilinear segment. And we have a rotation phi, function of W, exactly is W over R, which is a rotation, which will be subtracted by the general rotation. The second sketch represents as a uniform radial or transverse displacement, produces a dilation, additional dilation. You see this dilation epsilon, function of V is V over R. So please, the next, we see which is the result in the kinematic matrix. You see that we have the same, about the same in the curvilinear geometry, but shearing strain, axial dilation, and curvature. And we have three displacement. They are the same as for the rectilinear beam. Of course, we have always the derivatives on the diagonal. In this case, you see that 1 over r and -1 over r, as we can say, are the symmetric with the change of the sign. So, from these very important two examples, we see that the kinematic and the static operators are one the adjoint of the other. They seem to be the transpose only, but you see that we have to change the sign. So in mathematics, we say that they are one the adjoint of the other. So please, the next. The next case, the next slide that I don't see now. the next slide. Yes. The next slide is the rope. Yeah, I don't see my, yes, the rope. The rope, what means a rope? Is a beam with a flexural stiffness tending to 0. In this case, M, the bending moment and the shearing force are 0 by hypothesis. And so we reduce the problem to 2 equations in only one unknown, N, which is the axial force. The next, please. So we see now the 2 equation in a scalar form, N over R equal to 2, and the N in the S equal to minus P. What means that we have 2 equations. So this single unknown has to respect 2 different equations. So it means that you have to have the coincidence of the configuration of the beam with the thrust line or pressure line. No, which is we know that problem very well. But in this way, we understand that the rope is really hypostatic. It means that it's free to move. Please, the next. So we've had this training on this static kinematic duality because for our problem of shell of revolution and also thin domes is very important. So we have the same type of operator matrix form. The next, you see in the next slide, the formulation of the static equations. They are 3 equations in 5 unknowns. So it's hyperstatic, or we can better to say twice statically undetermined, indeterminate problem. The first equation is equilibrium to translation along the meridian, the second along the normal, and the third is the equation to rotation about the parallel. So I don't want, in this case, if you want, after my presentation, we can speak about that. But it's very interesting because they are all these 3 by 5, so 15 terms. Some are 0, of course, but it's interesting. Everyone has very important static meaning that I have no time to explain in the detail. You see that there is a -1, which is a similar meaning, for example, with respect to the beam problem that we have already seen. 3 equations and 5 unknowns are 2 membrane stresses along the meridian and along the parallel, the shearing force along the meridian, and the 2 bending moments. Please go to the kinematic problem. No? The kinematic problem, you see that according to the static kinematic duality, represented by this rectangular. In this case, it's not a square. You see, it is a rectangular because it's a 5 by 3 matrix, kinematic matrix. In fact, we have 5 deformations and 3 displacement. Exactly, the displacement U along the meridian, W along the normal, and phi is the rotation. So you see that we have a metric which is practically is the transpose of the previous one, except the algebraic terms which change their sign, algebraic signs. It's very interesting to look at in the third row, where we have 3 terms different from 0 in this case, because we have to obey duality. If we the next, please, the next. In the next slide, we can observe that the most classical treatment of the problem, due to chronologically to Flügge, 1934, Timoshenko, and Novozilov in the 40s, all 3 are the same terms practically, but the third row was absent. In some way, they didn't consider gamma S, which is, of course, the shearing strain along the meridian. And really, more generally, they didn't consider duality. even because at that time, maybe even we can say that computational methods were not yet developed. But it's not the cause. Even today, it's not very clear. This problem of duality is not very well known. Please, the next. So we arrive at the last topic that interesting for us: thin domes of membranes. Exactly as for the rope, we have to put equal to 0 what the flexural stiffness, and then the three static characteristics ms, m theta, the two bending moment, and ts. In this way, we have automatically two equations in two unknowns. You see, in practically, we can say that the problem is not hypostatic as for the rope, but is isostatic, and it could be resolved, as is very well known, only with the help of statics. About, we can also contemplate the problem of kinematics, the next. Yes, you see that also for kinematics, we have only the deformation that remains are the two membrane dilations, epsilon s, epsilon theta. We have the adjoint operator, very simple 2 by 2, and two displacement along the meridian and along the normal. So there is a duality. We can speak much longer about this interesting problem, but it's interesting to see that we have to do with a isostatic problem. So I go to the conclusion. Of course, now the first conclusion at least is that, as we have already said, that when the flexural stiffness goes to 0, tends to 0, we have that the arch problem, which is isostatic, drops to the problem of the rope, which is, excuse me, arch is isostatic, which is hypostatic. No? In the same way, from the shell of revolution, which is twice hyperstatic, we drop to the situation of the membrane or thin dome, which is isostatic. This is the first important conclusion. The second conclusion, which is the base for our computational investigation, is the next slide, is the last one. The last one, two remarks, important remarks. The first is that when the thickness is about 0, or not exactly maybe, but tending to 0, we have a strong implication due to this duality to implication to funicularity, which means membrane regime only. And when more realistically the thickness is different from zone 0, we have that we can obtain optimal we can say optimal shape when we minimize the flexural regime. So in some way there are the two main parameters. One is of course the shape, maybe the shallowness of the dome, and the other is of course the thickness. It is a strong coupled effects of the two parameters. So in some way this is introduction of the next paper or presentation where we have the pleasure to present numerical results. Thank you very much for your attention.
Okay, thank you so much, Professor Carpinteri, for your presentation. Very interesting. I ask if are there any questions, please?
May I?
Please, Francesco.
Okay. Yes, I've seen that Stefano also wants to ask, and maybe this is the same question, because we worked together on this topic. No, and so if Professor Carpinteri has some also some experience with the effect of boundary conditions, because he talked about the differential equation behind the shell structures, but also we have seen together with Stefano that boundary conditions also matters a lot.
on the funicularity, of course.
Yes, yes, of course, of course. Yes, in some way, if I can answer, no? I think that you are right. The third parameter, just to not put the thing in the most complex way, I didn't mention about the orientation of the constraint, maybe roles that may be oriented in an optimal way. Also in that case, for example, tangentially to the border of the shell, of course. So in some way, I think it's quite simple to say that the optimal orientation is the orientation for which the roller is the roller, maybe other of course constraints, but in that case there is not any problem. In some way we eliminate the problem. When there are of course fixed boundaries, means clamped or maybe yes, clamped at the border. The shell is clamped at the border. Of course, we have some we can say some area which is tending to zero, is shrinking when the thickness is decreasing, and where we have a flexural regime, of course. Yes.
Okay, thank you.
Other question, please.
Reality, my question was a little bit different, that maybe much more on request for a comment, an additional comment, because if you of course you are considering shells of revolution, and if you consider symmetric loads and with that symmetry of geometries, you anyway obtain so of course you have the equations that you shown in the case of membrane regime, but if you consider non-symmetric loads, for instance, you should have in any case a statically determinate problem, even if could appear shearing components in the membrane stress, in the membrane internal forces, but I'm not sure, and so I ask an additional comment in this way about the kinematics in this.
Yes. No. Yes. Interesting question, because of course you are right. I implicitly consider symmetry also for the loading. You are right. Just to put the problem in the simplest way. Of course, if we consider more general problem with not non-symmetry in the loading, or even not symmetry in the geometry, no, maybe a generic shell, no, generic shell or generic dome, membrane. You have to change very carefully the dimension of these matrix operators, which is in my book. So I studied this problem also some years ago, and I can tell you that the conclusion are about the same. So symmetry is not important. It's not so important for this this topic, I think, because the main conclusions are about the same, even if you have not symmetry. What is more likely maybe that you maybe have as a solution, optimal solution, a membrane solution, so funicularity, but part of it partially is intention. So not only compression as the civil engineer usually hope, but of course also the spherical domes have the bottom part is in tension, so it's not particularly strange what I'm saying. So in general, the funicularity or membrane states don't imply always compression. You have also tension, which is dangerous for concrete or we can say aggregative materials. But in general, what I hope to have answered your question. If you lose the symmetry, the conclusion are about the same. So it's not easy to say exactly, because you know, for example, I tell only this: when you have a generic shell, you have eight static characteristics and 5 displacements. So the degree of hyperstasis, the degree of redundancy is 3, not 2. But the conclusion are about the same. I hope to have interpreted your question.
Yes, I think that is much more about a discussion about this that, in my view, is very interesting because, as you know, I'm working on funicularity and this definition of R funicularity. And what I see is that if you start from the membrane regime, of course, you have ever a statically determinate problem in terms of equilibrium. Not the same, maybe if you just consider the compatibility equations. And maybe then you have to put together also to solve this problem in considering also what happens to the boundary of the shell. And maybe I know that Francesco, for instance, is working on this subject actually. And this is very important also when you consider the inverse problem of finding the optimal shape, because in what we see and what we saw in the literature and what we saw during this workshop is the membrane regime is generally the basic assumption, but in reality, because we cannot build curved surface without thickness, we also have moments, and we also have boundary conditions that are not optimal or optimized with respect to the fault finding conditions. Sometimes we also have different kind of load cases, and so I think this is a really interesting topic. And
you are right. My discussion is limited to the cases where the constraint effects are not so strong, of course. Yeah. You know, for example, the Isler paradigm that was maybe the first that systematically used this way of thinking, no? Because before Isler was not so well known, I think. In any case, not the practical way was not applied.
Anyway, thank you, because I think that the presentation was really clear and very didactic in a way for everyone.
Thanks.
Well, thank you so much. Are there any questions for our keynote lecturer? No? Very well. So I think that for IWSS, we have done with the fireworks. Very well. Now we can go to the last moment, the closing of our workshop. So I move to the presentation of the closing. Okay. Well, do you see the presentation? Yes.
Yes.
Yes. Yes.
Well, we spent another day full of interventions and rich of motivation for IWSS. It is my commitment to conclude first Italian workshop on shell and spatial structure, this last communication. I want to thank all the other co-organizers for this credit. So I take the burden and the honor to speak in the name of the whole organizing committee and scientific committee, expressing a great satisfaction for how the workshop has evolved and for the results that have been achieved in terms of inclusiveness and for the interest aroused in the covered topics. As you have seen, the workshop contained different works with a more theoretical cultural background that spanned showing numerical and experimental works and application without neglecting the design and the analysis of the existing structures. The first consideration from a global point of view lies exactly in the multiplicity of the topics covered. In our opinion, the workshop is laying the basement for the future work of IWSS community, able to express topics under the light of a right combination of two different souls, the academic mind, animated principally by the scientific interest, and the more design mind, devoted to achieve new futuristic application and technology. The IWSS topics covered many fields, by the way. The sustainability of existing large spatial structures, the design of versatile folding construction, the study of new construction system capable of reinterpreting the technique of the past under the light of contemporary technologies, the digital fabrication, of course, the monitoring system of shell and spatial structures, new and traditional form-finding methods and application, the optimization of pattern configuration, the concept of unicularity declined in different ways, the inspiration for shells by the natural and bee-inspired structures, the structural optimization methods for structures and components, the study of tensegrity structure and application to shell and space structures. I'm personally fascinated by all the works that I have seen in these 2 days, and I'm convinced that the adventure of IWSS must be absolutely to continue. At this point, I would like to thank first our magnificent 8 keynote speakers. We were very lucky that they accepted our invitation. They were able, with their interesting contents and with the passion that shines in people who love their work, to increase enormously the value of the workshop. The IWSS keynotes represents a great value for us, not only because they are important scientists and designers for all our community, but also because they have been directly and in different ways give the inspiration for us, the organizers. We were very lucky that they accepted our invitation. They were able, with their interesting contribution, to give us a lot of. I think that special greetings and special acknowledgements go to Sigrid Adriansens. Sigrid, you have been able to inspire each of us, and we believe that the workshop would not have been the same without your help. I would also to thank the International Association of Shell and Spatial Structure, IWSS, and in particular, Professor Carlos Lazaro for his work. We believe, in fact, it is essential for IWSS to be strictly in contact with IASS community. IASS helped us to create an innovative possibility to spread the studies that we love even more widely in our country. In addition, I wanted to thank Professor Luciano Rosati for the participation and for the words he said on behalf of the Società Italiana di Scienze delle Costruzioni. The awareness of having a sharing and support from an association so representative of the Italian scientific and academic world is for us a further strong push to do even more. Finally, I would like to thank all the participants, the authors, the co-authors, and the speakers. With special thanks to all foreign authors who have been able to get the scientific spirit at the base of all the meetings that have a successful outcome, the absence of boundaries. It is right before closing to give some numbers of the workshop that is ending. In the online experience, we had an average number of people connected at the same time of 60 on the Zoom platform and 80 during YouTube streamings, with peaks above 150 watchers during the keynote presentations. Over 650 distinct users have watched each live on YouTube channel, IWSS2020. The virtual tour devoted to Torino Esposizioni and the architecture of Pierluigi Nervi exceeded 400 views in 4 days. Thank you so much. We thank you very much for these results, really. I want to close now before I get to boring for you, but I wanted to do with a promise. I was with Francesco, Andrea, and Stefano, one of the most active fans of the online mode, and I am happy that nowadays there are robust specific tools allowing this wonderful experience. But I hope that the time of social distancing are about to terminate. For this reason, we sincerely hope to meet you for the next IWSS appointment in person. In agreement with the other co-organizers, I can communicate you that, with my great pleasure, the next IWSS will be held in Turin in presence. So I can personally show you the place of meanings and the architecture that have been mentioned during the opening session and during the workshop itself. As for the dates of the next event, you still have to be patient. The creation of expectation, in fact, is a communication technique. No, I'm joking, of course. In order to be able to be careful over the actual period, we must understand how the restriction relating to COVID pandemic will evolve in the next month. For this reason, stay connected with our communication channels and the website, because as soon as we have some news, we will invite you to the next IWSS appointments. Finally, I would like to remind you that if you wish, you can send a paper that will be part of a specific special issue in the magazine Car and Layered Structures. First deadline for the submission is the 31 of July 2020. Please be punctual with this in order to simplify the guest editor management and consequently to speed up the revision procedures and consequent possible publication. Thank you as much for everything. And I remind you not to go away. We have to toast all together in the online toast. Thank you again. And here you have the rules for the online toast, of course. The first two are recommendations that I want to do. The first is you cannot know wine by the barrel, of course. The second is that life is too short to drink bad wine. And the third is very important. Don't worry, drink as much as you want. You should be at home. And it's Friday evening, of course. That's all.
I think that also myself, Francesco and Andrea, so I start myself, I would like to thank Amedeo for these very emotional words, and all the participants, all the attendees, ISS, Cisco, okay, everyone. So really, really thank you from my side. Please, Francesco.
Okay, thank you, Stefano. I want to thank Stefano, Andrea, and Amedeo because they have been friends more than colleagues in the preparation of IWSS, but also I wish to thank every speakers and keynote lecturers because it is their merit if this workshop has been so successful. So thank you. It's your turn, Andrea.
I join you guys in thanking everybody, as keynote speaker, participants and listeners, and you, of course. And just to finish, the day before the workshop, my biggest nightmare is that tomorrow nobody can manage to get in the connection with these numbers, these codes. They are wrong. We made some mistakes. Anyway, everything went well. We are very happy. Thank you very much.
I think now, Amedeo, it's very important to close the streaming.
Yes, yes, of course.
And I would like to invite everyone